Welcome back to linear algebra. Today we're going to talk about basis and dimension. First, we define what it means for vectors in general vector spaces to be linearly independent. Set S of vectors is linearly independent if for any finite subset of S, V1, V2 through Vn, the only solution to C1V1 plus C2V2 plus CnVn equals the zero vector is all of the coefficients equal to 0. In other words, a set of vectors is linearly independent if and only if, because definitions are always if and only if statements. Every linear combination of elements of S that give you the zero vector will have 0 coefficients. Also, what does it mean for a collection of vectors to be linearly dependent? Well, it's linearly dependent if it is not linearly independent. Okay, I know that's pretty smart-ass. So, what does that mean? Id est there's a finite subset V1 through Vn and constants C1 through Cn, not all 0, such that there's a linear combination equal to the 0 vector. Let's look at the following collection of vectors. Let's have 1, 1, 0, 2, negative 1, 2, and let's see, how about 0, 3, negative 2. Is this collection of vectors linearly independent or linearly dependent? Well, if you can find a linear combination of these that gives you the 0 vector, they're linearly dependent. Otherwise, they're linearly independent. There is an easy way to tell. I guess on this particular set, you can see that 2 times the first vector minus the second vector is equal to the third vector. So by inspection, you can see that 2 times 1, 1, 0 minus 1, or plus negative 1, times 2, negative 1, 2, equals this, so minus 0, 3, negative 2 equals 0, 0, 0. So there is a linear combination that gives you the zero vector. However, I want to do this a different way so you can see what to do if you can't see it by inspection. As we know, we're supposed to have some kind of linear combination that gives you the zero vector, which is equivalent to solving a matrix equation AC equals 0. A would be the matrix with columns 1, 1, 0, 2, negative 1, 2, 0, 3, negative 2, and then we can make an augmented array with all zeros on the other side. All we have to do is find the reduced row echelon form. First, let's take negative 1 times the first row and add to the second row. This gives us 1, 2, 0, and then 0, negative 1 times this plus this, we get negative 3, 3, 0, 0, 2, negative 2, and 0. Now, we can multiply the second row through by negative 1/3 and this last row through by 1/2. So negative 1/3 row 2 yields a new row 2, and 1/2 row 3 yields a new row 3. We'll have 1, 2, 0, 0, 1, negative 1, 0, 1, negative 1. And then if we take negative row 2 and add to row 3, yielding a new row 3, we'll have a row of zeros across the bottom. I'll just cross it out, indicating it's a row of zeros. When you have a row of zeros, you can see that we have a free variable. Because we have a free variable, there are infinitely many solutions. There's always at least one solution. The constant's all zero. The question is there something with constants not all zero? In this case, the answer to that question is yes. We will be able to find infinitely many solutions, as a matter of fact. This situation is characteristic of the case where the vectors are linearly dependent. You can see we'll have C3 equals anything you want because it's the free variable. Let's call it t. Then C2 will be t, and C1 will be minus 2t. So the vector C will be anything of the form t times negative 2, 1, 1. The combination that we had earlier corresponds to the choice of t equals minus 1. We had 2 minus 1 minus 1. All you need is for one non-zero vector c to satisfy this equation to deduce that the vectors representing the columns of the matrix A are linearly dependent. It's linearly dependent. Before moving on, I want you to observe something. Let's set W to be the span, the set of all linear combinations, of the first two vectors in this set. Note, the third vector is already a linear combination of the other two. That means the third vector, 0, 3, negative 2, is an element of the span of the first two. In some sense, the first two vectors already encode all of the information in the third vector. It's as though this is superfluous. It's unnecessary. Let's toss it out. It doesn't give us anything new. What if we pared this set down and formed a set, let's call it S prime, 1, 1, 0, 2, negative 1, 2. We know that this set has the same span as the larger set. Because we can construct this vector, we can construct all other linear combinations of the first three vectors. The question I have now is this paired set linearly independent? Well, let's check. Let's put these into an augmented array with just zeros down the last column and see if the coefficients C1 and C2 must be 0. We'll perform an elementary row operation. Negative row 1 plus row 2 yields a new row 2. We obtain 1, 2, 0, 0. Let's see. Negative 1 times this plus this, negative 1 times this plus this, we get negative 3, 0, 0, 2, 0. At this point, we can multiply the second row through by negative 1/3, and 1/2 row 3 yields a new row 3. We have 1, 2, 0, 0, 1, 0, 0, 1, 0. We can take negative 2 times row 2 plus row 1 yields a new row 1, and negative row 2 plus row 3 yields a new row 3. This gives us 1, 0, 0, 0, 1, 0, 0, 0, 0. We have C2 equals 0 and C1 equals 0. The only solution where I have a linear combination equal to the 0 vector is the trivial one, where the coefficients are 0. This is exactly the situation where we say that these vectors, the first two, are linearly independent. We conclude that S prime is linearly independent. We can pair linearly dependent sets down to the point where what's left over is linearly independent. The paired set will span exactly the same set as the original collection. We make the following observation. Set W to be the span of V1, V2 through Vn, and suppose Vn is a linear combination of V1, V2 through Vn minus 1. So the last one can be already combined using the other vectors. We can construct it from these by a simple linear combination. Then if W prime equals the span of V1, V2 to Vn minus 1, everything except for that last vector, then W prime and W are the same thing. They span the same set. In the next example, I want to compare the column spaces of two matrices. First, 1, 1, 0, 1, 0, 1, 0, 1, 1. And another matrix, we'll call it A tilde, which is 1, 1, 0, 1, 0, 1, 0, 1, 1, 3, 2, 1. How do the column spaces of these matrices compare? First, you need to remember what a column space is. The column space of a matrix A is the span of the columns. We'll call those A1, A2 through AN, the set of all linear combinations of the columns of the matrix. In other words, find all vectors B such that AC equals B for some vector C. For the first matrix, we'll see if AX equals some vector B, we'll set B to be ABC. We'll see whether or not this is consistent. If this system is consistent for an arbitrary vector ABC, then it will span all of R3. Every vector in R3 can be expressed as a linear combination of the columns in the matrix A. Let's see if that's true. Is this system consistent for all? An upside down capital A is the logical quantifier for all vectors A, B, C. That's our question. All we have to do is find the reduced Row-Echelon form. I obtained the reduced Row-Echelon form of 100 A plus B minus C all over 2, 010 A minus B plus C all over 2, and 001 negative A plus B plus C all over 2. This is easy to check from the original equation. What we see is that the system is consistent. We find that there is a unique way of expressing an arbitrary vector A, B, and C as a linear combination of the columns of the matrix A. Because the matrix A tilde only throws in one last vector, note that the vector 3, 2, 1 can be thought of as an ABC. Since every vector ABC can be expressed as a linear combination of these first three, then 3, 2, 1 can be expressed as a linear combination of the first three. That means the columns of matrix A tilde are linearly dependent. We have this vector in the last column that can be expressed as a linear combination of the vectors in the first three. That implies then that the column spaces of A and A tilde are the same by the last theorem. If you have one vector that's a linear combination of the others, the spans of the sets will be identical. The span of the columns is the column space by definition. We have the column space of A is exactly the same as the column space of A tilde. Here's our idea. If we start with a linearly dependent set S, then toss out those dependent vectors, the vectors that can be expressed as linear combinations of the others. One by one, until what is left over is linearly independent. at each step, what is left over will span the same space. Will have the same span, in other words. Also note, if the set S is linearly independent, then each vector in the span may be uniquely expressed as a linear combination of elements in S. We're trying to get at the question, given some vector space, what is the minimum number of vectors that it takes to reconstruct every vector in that vector space by constructing a span? We already know that the span of 1, 0, 0, 1 is all of R2. We can use two vectors to construct R2. Also, the span of 1, 0, 0, 0, 1, 0, 0, 0, 1 is all of R3. It takes these three vectors to construct every vector in R3 through simple linear combinations. How many does it take in general for an arbitrary vector space? If a space is linearly dependent, you can get by with fewer vectors and span the same set. If the set is linearly independent, it may not span the whole space. Consider this. What's the span of the set that contains 1, 0? Well, it's the set of everything of the form x0 such that x is a real number. In other words, the x-axis in the xy plane. It doesn't span the whole space. It only spans some proper subspace. So if our goal is to find the minimum number of vectors necessary to construct a vector space through linear combinations, linear independence isn't enough. It also has to span. We're going to make a definition. Sometimes we don't use the first word, so I'm going to put it in parentheses. A Hamel basis B of a vector space V is, it has to be linearly independent, spanning set for V. That means B, the basis, has to be linearly independent, and the span of the basis gives us the entire vector space. I should mention that there are other notions of basis that you might encounter in the future, like the Schauder basis, but in most classes, but this notion of basis is so common that we often drop the name Hamel and just call it a basis. As you can see, there are two conditions to be a basis. The set must be linearly independent, and it must span the space. As an example, consider the set B 1, 0, 0, 1. This set is linearly independent, and the span of B is all of R2. Therefore, B is a basis for R2. With these two vectors alone and the ability to calculate linear combinations, we can construct every other vector in R2. However, I should caution that a basis for a vector space is not unique. Suppose we have 1, 1, and then 1, negative 1. First of all, is this linearly independent? We can tell by seeing if some linear combination that is non-trivial gives you 0. Solving AC equals 0 is equivalent to finding the reduced row echelon form on this augmented array. Let's work on this. We'll take negative row 1 plus row 2 yields a new row 2. That gives us 1, 1, 0, 0, negative 2, 0. And then clearly, through two more elementary row operations, we can express this as follows. This will be C2 equals 0, and the first row represents the equation C1 equals 0. Since the only linear combination that gives you the 0 vector is the trivial one, we deduce that the set B is linearly independent. But that's only half of what it takes to be a basis. To show that B is a basis, we have to show that the matrix A having columns 1, 1, and 1, negative 1 has a solution AC equals B. There's a linear combination of those columns giving you B, where B is an arbitrary vector AB. In other words, we need to prove the consistency of the system of equations. So let's calculate the reduced row echelon form and see if we can show that it is consistent. Let's see, 1, 1A, negative 1 times this plus this, we'll have 0, negative 2, and then B minus A. We'll divide by 2, negative 2, giving us a 1 in this spot, and then negative 1 times row 2 plus row 1. Let's see, we'll have A minus B over 2, and 1, 0. Negative 1 times this plus this. We'll push the negative through here. Negative 1 times this plus this, we'll have negative 1 times this plus this. You can see that we'll get A plus B over 2 here. If we add these two, we get A. If we subtract them, we get B. So we see that there always is a solution to this system. C2 will be A minus B over 2, and C1 will be A plus B over 2, by which we can construct any vector AB in R2. We deduce that because this is consistent, that the span of B will be all of R2. Any vector in R2 can be expressed as a linear combination. Since the set was linearly independent, and since it spans R2, it is a basis. You can see that there isn't just one basis for a given vector space. There can be many. The idea being that in order to span the entire space R2, you need some vector V1 and some other vector, say V2, poking out in a different direction. If they're in the same direction, the span will just be in that one line. To span the entire space, we can construct other vectors by taking linear combinations of these two. Any vector can be constructed by rescaling of these two vectors. Some scalar times this, some scalar times this, gives us the ability to construct any other vector in the entire plane, as long as these two vectors poke out in new directions, in independent directions. Recall that in Rn, E1 is the vector 1, 0, a bunch of zeros, E2, 0, 1, zeros, etc. En 0, 0, 1. This is called the standard order because we're placing it in exactly this order basis, or the SOB for Rn. It is linearly independent, and every vector in Rn can be constructed by taking a linear combination of these. It's a linearly independent spanning set. That's a basis. So it is a basis. It's the standard basis. Standard bases are selected by some arbitrary choice. It is conventional, and it's in the correct order, the standard ordered basis. What is the SOB for Pn? The set of polynomials of degree n or less. The standard ordered basis is 1, x, x squared, up to xn. By taking a linear combination of these functions, we can construct any polynomial in Pn. Let's show that b, which is 1 plus x squared 1 minus x squared x, is a basis for P2, a set of polynomials of degree 2 or less. In other words, first of all, is it linearly independent? And does it span the space? We have to check those two steps. First of all, are these functions, these vectors, linearly independent? So we'll construct C1 times 1 plus x squared plus C2 times 1 minus x squared plus C3 times x, and set that equal to the 0 polynomial, 0 vector. The 0 vector in P2 is the 0 function, which we'll denote by 0. So you can see the constants are C1 plus C2. There's only one coefficient of x, and that's C3, and then the coefficients of x squared are C1 minus C2. The only way two polynomials equal each other, we do have a polynomial on the left, and the 0 function is a polynomial on the right. The only way one polynomial equals another polynomial is if corresponding coefficients are equal. All the coefficients of the 0 polynomial are 0. So we get three equations. C1 plus C2 is 0, C3 is 0, and C1 minus C2 is 0. Well, C3 is 0. We have that. Note that if you add the first and the last equation, you get 2C1 is 0, which implies that C1 is 0. And then if you subtract them, you get 2C2 is 0, which implies that C2 is 0. We have all of the coefficients equaling 0. The only linear combination of these vectors that gives you the 0 vector is the trivial one. That means linearly independent. We still have to check that it spans P2. To see that, we need to show that there are coefficients C1, C2, and C3 so that we can construct any polynomial in P2, which we'll denote by a plus bx plus cx squared. This gives us three equations. First of all, let's rewrite the left-hand side as C1 plus C2 plus C3x plus C1 minus C2 x squared. We have to equate coefficients on each side, so we'll have C1 plus C2 equals A, C3 is B, and then C1 minus C2 equals C. As you can see, C3 is B. If you add the first and the third equations, you'll get 2c1 equals a plus c. That means c1 is a plus c divided by 2. And then if you subtract, you'll get 2c2 is a minus c. That means c2 is a minus c over 2. So we get consistency. We find that there are constants c1, c2, and c3 by which we can construct an arbitrary polynomial a plus bx plus c squared in P2. We deduce then that it spans. For a set B to span a vector space V means for the span of B to be equal to V. Finally, we can conclude that B is a basis for the vector space P2. It's not the standard ordered basis. The standard ordered basis is 1x and x squared. But it is a basis. It is a linearly independent spanning set. Here's an important question. Does every basis for a given vector space have to have the same number of elements? For instance, does every basis for R2 have to have 2 elements, just like the standard ordered basis? That's an important question to answer. We'll answer that in the following theorem. If B equals V1 to Vn is a basis for a vector space V having n elements, so this basis has n elements, then every basis for the vector space V has n elements. So the answer is yes, every basis must have exactly the same number of elements. The proof is a classic Reductio ad Absurdum proof. In a Reductio ad Absurdum proof, you assume the opposite of what you would like to prove, and then show that that leads to some logical absurdity. If the opposite of what you wanted to show is false, then what you wanted to show must be true. We'll assume B1, which is V1 through Vn, and B2, which is W1 through Wm, are bases, that's the plural of basis, for a vector space V, and we'll assume that n isn't m. Without loss of generality, we're going to suppose that m is strictly larger than n. We will show that B2 is linearly dependent, contradicting that it is a basis. First of all, note that B1 is a basis, so it spans the entire vector space. That means every element in V2 may be expressed as a linear combination of elements in B1. We can write Wj, the jth element in basis B2, as a sum, as I goes from 1 to n of some constant, which I'll call Aij Vi. Well, these j's are the j coefficients for wj, and there are going to be n of those coefficients covering all of the vectors v1 through vn. Aha. Consider the following equation. A linear combination equal to the zero vector. Each of these w's can be represented in terms of the v's. We'll have the situation as follows. C1 times the sum as I goes from 1 to n of AI1 VI plus the Cm times the sum as I goes from 1 to n of A I n VI. Well, we can actually express this as kind of a double sum, if you will. This is the sum of these various sums. You can write this as the sum as j goes from 1 to m of Cj times the sum as I goes from 1 to n of A I j VI. This gives us, interchanging the sums and distributing the Cj's, the sum as I goes from 1 to n of the sum as j goes from 1 to m of Cj A I j. We might write this in the reverse order, A I j Cj, because then it's proper matrix multiplication, Vi. You can see that what we're getting here is for a fixed I, we're getting the ith row of the matrix A times the column vector C. So we're taking the rows of the matrix A and multiplying onto C. That's what you do when you multiply a matrix times a vector. All of this, remember, is equal to 0, and this is a linear combination, with these being the constants, of the vectors v, the vectors in V1. Since V1 is linearly independent, we see that all of these coefficients must be 0. For each I. Now, that gives us a system of equations. Each different I gives us a different equation. The critical question is, how many equations in how many unknowns? The unknowns being the Cj's. The index I runs from 1 to n. That means we have n equations. The index j runs from 1 to m. There are m unknowns. The matrix A is n by m. C is m by 1. You end up with something that is n by 1, of course, but the critical point is that n is less than m by hypothesis. The number of equations is strictly less than the number of unknowns, and this is a homogeneous system. We're solving this equal to the 0 vector. Now, if a linear system that is homogeneous is underdetermined, like this case, not only do you get the trivial solution, but there will be non-trivial solutions as well. which means there are coordinates Ci or Cj that are not zero that will solve this homogeneous system of equations. But that implies that set B2 is linearly dependent. Which contradicts the hypothesis that B2 is a basis. Basis has to be a linearly independent spanning set. So some hypothesis that we have made is false, but the only hypothesis up for question is the hypothesis that M is strictly larger than N. We deduce then that N is not strictly smaller than M. We deduce then that it is not true that N is strictly smaller than M. But that only tells us that N is greater than or equal to M. However, this conclusion is based upon the hypothesis that we had before, that N was less than M. If we make the assumption the other way around, then we will conclude that N is less than or equal to M. Both of these must be true, and the only way they can both be true is if N equals M, and that is the end of the proof. Every basis for a vector space has exactly the same number of elements, at least in the case that the vector spaces are finite dimensional. Because every basis for a vector space has exactly the same number of elements, that allows us to define what we mean by the dimension of a vector space. The dimension of a vector space is the number of elements in a Hamel basis. There is an idea called the fractal dimension. If we start off with a square in space, if we wanted to double the size, how many copies would it take? To double the size, you need 4 copies. If we had a cube and we want to double it, how many copies does it take? In this case, 1, 2, 3, 4, 5, 6, 7, 8. It takes 8 copies. To double the size, it takes 2 on the exponential function with base 2. 2 to the power 2 is 4. In cubes, in 3 space, 2 to the power 3 is 8. If we're just dealing with a length and we want to double it, 2 to the power 1 will double it. We're in dimension 1 if we just have lengths. If they're regions in the plane, we're in dimension 2. If we have cubes, we're in dimension 3, and so on. We have some notation. The dimension of a vector space V is denoted by dim of V. Also, note, if a vector space consists only of the zero vector, by convention, its dimension is 0. So if it's just a point, the zero vector, then the dimension is 0. And the dimension of Rn is n, the number of elements in the standard ordered basis. The dimension of Pn is n plus 1. Yes, you go all the way up to xn in a basis, but you start at 1, which is x to the power 0. You have that extra term, so you get n plus 1 elements in a basis for Pn. What about the dimension of M, N, M? The set of n by m matrices? Well, that's n times m. Now, a vector space is finite dimensional if and only if it has a basis having a finite number of elements. In which case, every basis will have exactly that finite number of elements. As a quick example, consider P, the vector space of all polynomials. It has a basis, 1, x, x squared, and so on forever. This basis is not finite. Since this vector space has a basis that's not finite, and no basis will be finite for it, then it is not finite dimensional. If a vector space is not finite dimensional, then it is infinite dimensional. The vector space of polynomials is infinite dimensional. And there are many other vector spaces that are infinite dimensional. There are a couple basic facts about bases that you need to know. First of all, suppose that V is a vector space of dimension n. First, if S is a set containing n vectors, the same as the dimension of this vector space, and S is linearly independent, if you have n linearly independent vectors in an n-dimensional vector space, then S spans V so that S is a basis for V. That tells you if you have n linearly independent vectors in an n-dimensional vector space, then it is automatically a basis. It will span. Second, if S is a set having n vectors in an n-dimensional vector space V, and let's suppose that the span of S is all of V, then S is linearly independent, and so S is a basis for V. you can see that you only need one of the two conditions to hold if you already know the dimension of the vector space and you have that many vectors in a set. If it's linearly independent, it automatically spans. If it spans, it's automatically linearly independent. Either way, you get a basis by just checking one condition. In our proof for property 1, we'll suppose our set V1 through Vn is linearly independent, but the proof is going to be by contradiction, i.e. a Reductio ad Absurdum proof. So we'll also suppose that the span of S is not all of V. Since it doesn't span all of V, let W be in V, W not in the span of S. Then the set S hat equal to V1 through Vn, and we'll toss in W, is linearly independent. There's no way that you can express W as a linear combination of the vectors V1 through Vn. So this set must be linearly independent. But the dimension of the vector space is n, which means each of these vectors can be expressed as a linear combination of elements in a basis, and that basis will have n elements. That will give us n plus 1 equations. That will give us n equations in n plus 1 unknowns, the coefficients of the vectors. That's underdetermined, which means there are infinitely many solutions, which means that this set is dependent. That's a clear contradiction, so an assumption that we've made must be false. That assumption can only be that the span of S is not V. Therefore, the span of S is V, and that means S is a basis. The proof of part 2 is also by contradiction. Reductio ad Absurdum. Suppose S is V1 through Vn. The span of S is all of V, but S is linearly dependent. Then we may remove dependent elements one at a time to obtain a smallest set that still spans the same space, one by one, until we have a minimal set S hat that still spans all of V. We're assuming dependence, so removing a dependent vector will maintain the span. We'll still be able to span the entire space, but is linearly independent. We have to get there eventually, because eventually we will only have one vector left. Then the S hat that remains is a basis, but has less than n elements. That's a contradiction, and we deduce then that the assumption that S is linearly dependent is wrong. and it must in fact be linearly independent and hence form a basis. And that's the end of the proof. For example, show that S equals 1, 1, 1, negative 1 is a basis for R2. We have our choice. We can either show that this set is linearly independent or that it spans. We don't need to show both. R2 is dimension 2 because the standard ordered basis has 2 elements. The set S has 2 elements. We only need to check one. So let's check that it is linearly independent. In other words, do there exist constants C1 and C2 that are not 0 that give you the 0 vector, or do C1 and C2 have to be 0? We get a system of equations C1 plus C2 equals 0 and C1 minus C2 equals 0, which of course becomes the augmented array given by these vectors down the column and 0 down the last column. We find a echelon form, 1, 1, 0. We'll subtract 1. We'll get a 0 here, a negative 2 here, and then 0. So negative 2 times C2 is 0. That means C2 is 0. If C1 plus C2 is 0, that implies C1 is 0. Since the constants have to be 0, we deduce that it is linearly independent. Therefore, it is a basis. Is the set B, I'll say suggestively, 1, 1, 1, 0, 2, 3, a basis for R2? The answer is no. The number of elements in B is 3. That's called the cardinality of the set. The cardinality of B is 3. That's not 2. The dimension of R2 is 2. Every basis has to have exactly 2 elements. Therefore, this is not a basis. Is S equals, let's say, 1, 1, 0, 2, negative 1, 3, a basis for R3? Well, no. The cardinality of this set is 2, which is not 3. Therefore, this is not a basis. Every basis for R3 has to have exactly 3 elements. In our next example, I ask, is the set S equal to x squared plus 2x plus 3, x squared plus 7x plus 8 a basis for P2? Recall that the dimension of P2 is 3. The standard ordered basis is 1x x squared. Therefore, nope, this is not a basis. The set has cardinality 2, and so it can't be a basis because every basis has cardinality of 3. In our last theorem, which we'll call a corollary, corollary is a theorem that is a consequence of another theorem. We'll say, suppose V is a vector space. It has dimension n. And S is the set V1 through Vk, k strictly less than n. And suppose this is linearly independent. then we may extend S to some set S hat, V1 to Vk, and then adding in vectors Vk plus 1 to Vn, so that S hat is a basis. If you don't quite have enough vectors to form a basis, but you are linearly independent, then you can keep throwing vectors in and eventually get a basis.